This year's theme for 2024 is titled Tech Transformation, Shaping the Future of Society, Education, and Industry. November to Remember is a wonderful initiative started by Dr. Celestine Wendy. It's done basically to increase the research culture at the University of Bolton by calling esteemed speakers to speak on various domains. And this is not just related to our career, it's also related to us as individuals, because you see topics related to domains in computer science and you see topics relating to domains in professional practice. This week not this week, today, we'll be talking about machine learning, and we have the distinguished speaker, Dr. Vishnu Pendyala. And I would do a brief summary of his bio. Dr. Vishnu Pendyala is a faculty member in Applied Data Science and an academic senator with San Jose State University, United States. He is the current chair of the IEEE Computer Society Santa Clara Valley Chapter and IEEE Computer Society Distinguished Contributor. During his 3-year term as an ACM Distinguished Speaker, and before that as a researcher and industry expert, he gave numerous 70-plus talks in various reputed forums such as Faculty Development Programs, the 12th IEEE GHTC, the IEEE ANTS, the 12th IACC, the 10th ICMC, IUCEE, to audiences at venues such as Stanford University, University of Bolton, and so forth. Some of these talks are available online on YouTube and on IEEE.tv. He is a senior member of the IEEE and has over 2 decades of experience in the software industry in the Silicon Valley, USA. His book, Veracity of Big Data, is available in several libraries, including those of MIT, Stanford, CMU, the US Congress, and internationally. 2 other books on machine learning and software development that he edited are also well received and found place in the US Library of Congress and other reputed libraries. Dr. Pendyala taught a 1-week course sponsored by the Ministry of Human Resource Development, Government of India, under the GIAN program in 2017 to computer science faculty from all over the country, and delivered a keynote in a similar program sponsored by AICTE, Government of India, in 2022. Dr. Pendyala recently served on the US government's National Science Foundation, NSF, Proposal Review Panel. He received the Ramanujan Memorial Gold Medal and a shield for his college at the State Math Olympiad. He also played an active role in Computer Society of India and was the program secretary for its annual national convention. And more importantly, Dr. Pendyala was also spoke in the previous November to Remember talks. Welcome, Dr. Pendyala.
Thank you, Lair. That was a very generous introduction.
It's good to have you again.
Yeah, it's a pleasure to be back with you all.
Okay. So without further ado, you can begin your lecture, Dr. Pendyala.
Yeah, sure. I'll start sharing my screen. Everyone able to see my screen, right? Yes, thank you. Thanks for the confirmation. So, so today's topic is explainability of artificial intelligence and machine learning models for a socially sustainable growth, artificial intelligence growth. We know AI ML is really booming, and it will continue to drive the economy in the coming years, and is likely to be in control for many years to come, and of many domains and life-critical tasks. So just like we want our governments, leaders, and everyone in control to be transparent, we want the AI ML models also to be transparent. Social sustainability will be adversely impacted otherwise, and there will be increasing resistance to the adoption of AI ML. We already see quite a bit of resistance from quite a few quarters, some cautions and some warnings and things like that. So there will be increasing resistance if, and then it will jeopardize our social sustainability if the models are not explainable. So that is the topic of today's session. So let's start with this recent news about the godfather of artificial intelligence winning the Nobel Prize. In this New Yorker article, there's a profile of Jeffrey Hinton, this year's Nobel Prize winner. He is afraid that we may lose control over the artificial intelligence models that we are building. So the title of the article is "Why the Godfather of Artificial Intelligence Fears What He Has Built." So it reminds me of one famous quotation: "We fear what we don't understand." So this is spoken by the character of Dr. Jonathan Crane. I believe in the movie is called Scarecrow in the Batman Begins movie. So indeed, we can't drive a car if we don't understand why it took a right turn or a left turn or a U-turn, right? So being able to explain and interpret the tools that we use is critical to their usage. So that is the reason for explainability of AI ML models. And more importantly, AI makes mistakes. So it's not foolproof. It's not entirely accurate in its behavior. So the lack of explainability is a cause of worry that it may go out of hand, right? But the mistakes that AI makes make it even more compelling to call for explainability. So first thing is it decides unfairly. The models are sometimes biased. It has been proven, and it has the adverse effects of its bias have been in news quite widely. It overfits, causing privacy concerns. In my last year's talk at November to Remember, I covered this topic of overfitting and privacy concerns and things like that. You can watch the video if you're interested. And it hallucinates. AI models hallucinate, giving incorrect answers. So this is a big problem. Most of you would have observed this with when using large language models like ChatGPT or Copilot and Gemini, for instance. They all hallucinate. Things have become much better now, but a few years back it was really worse. I mean, a couple of years back it was really worse. And often no one can accurately explain its behavior. So with all these issues, there is certainly a reason to worry, right? Particularly the last reason. So earlier this year, we published a paper on mental health prediction. I believe University of Bolton psychointelligence that started focus. I mean, there is a focus of this institute on psychointelligence. So that also focuses on using artificial intelligence for mental health issues. So for this paper, what we did was we took a data set on which several researchers published papers claiming outstanding performance of models in predicting mental health. Of course, we also got outstanding results when we used those models. But what we found when we started explaining the model's behavior was not intuitive at all, as we will see later. So that is the reason why in the paper we concluded that this work proves that merely achieving superlative evaluation metrics can be dangerously misleading and may infringe upon ethical horizons. A future direction is to investigate methods to quantify the effectiveness of machine learning models in terms of insights from their explainability. So not just me, but several other researchers also found similar issues with relying on performance metrics alone. So for instance, in this paper, Explainable AI for Android malware detection towards understanding why the models perform so well in 2022, the authors claim that our results indicate that machine learning models classify malware based on temporal differences between malware and benign rather than the actual malicious behaviors. So the features they were focusing on were not at all relevant. So they're focusing on temporal differences. And then they also say that we discover the temporal sample inconsistency in the training dataset brings over-optimistic classification performance, up to 99% F1 score and accuracy. So they also found that accuracy is not a good measure, and we need to understand how these models arrived at the predictions and at that superlative accuracy. Here's another. So in this paper, to what extent do deep neural network-based image classification models make unreliable inferences? Published in a journal called Empirical Software Engineering. The authors say that we applied our approach to 18 pre-trained single-label image classification models and 3 multi-label classification models, and then examine their inferences on the ImageNet and COCO dataset. We found that unreliable inferences are pervasive. Specifically, for each model, more than thousands of correct classifications are actually made using irrelevant features. So hope that convinced you about the need for explainability and the fact that accuracy alone is not sufficient. The evaluation metrics are not sufficient. There are many others like this, so much so that the European Union law back in May 2018 itself mandated explainability. So, so there is a implicit right to explanation in the GDPR. GDPR stands for General Data Protection Regulation, right? It's one of the most, I think it's one of the finest legislation in the world of data, I think, in my opinion, at least. So in this GDPR recital 71, it says a phrase or part of the sentence states that to obtain an explanation of the decision reached after such assessment and to challenge the decision. So, so this is in a recital, and the authority of the recital is non-binding under European Union law, but it still provides a critical reference point for future interpretations. So if the court goes to the Supreme Court, then the judges can get to interpret. Even in the lower courts, it is subject to interpretation. Moreover, Articles 13, 14, and 15 of the GDPR clearly state that of automated decision making, including profiling, referred to in Article 22(1) and 4, and at least in those cases, meaningful information about the logic involved. So this again is implicit requirement for the right to explanation. So that's when, excuse me, that's when the model explainability comes into picture. So how do we explain the behavior of a machine learning model? So let us first consider a typical example and see how people and then machines explain their decisions. So let us take the example of credit applications. So somebody's credit has been denied. So this is a common application in the industry and academia. I used to give this as a homework assignment to my undergrad students who studied machine learning. But there's a very big problem. People can commit suicides if their credit applications are denied in a critical situation. We have read in news, particularly in certain countries, that people have actually um, uh, so typically I read in the news that farmers in India committed suicide because of their financial situation and inability to get credit. So this is a serious problem. So if the problem escalates to the court, banks need to give an explanation. And so let us look at some of those explanations that people can give. So they can say that the applicant had a poor credit score. He or she had a history of late payments and defaults. So that's why the credit was denied. Or insufficient income. Applicant's income is too low relative to their existing debt and living expenses. Or they could say that there are too many open credit accounts. Applicant had multiple credit cards and loans. So ability to manage additional credit is questionable. So that is the reason why the credit was denied. And more, there could be many such reasons. So for instance, if they say that it is because the applicant is too old or is of this gender, this religion, or this ethnicity, this skin color, then the decision can be challenged in a court of law for bias and discrimination. Right? So that is the intent probably behind the GDPR, right? We want to be able to detect or understand how the machine learning model came to that decision and then be able to challenge it. So let us see how machine learning does this. So what are, first let us see what the target variable is. What is the target variable? So the target variable is whether the credit application is approved or not. So that is the last column in the data set. The data set is like a table, and the last column of the table is whether the credit application has been approved or not. And what are the features based on which the machine learning model adjudicates the application? So the features are quite similar to what the human beings used. So the features could be gender, age, debt, marital status, bank customer. So these are all the fields that an applicant fills in the application form. So whether the person is a bank customer, their education level, ethnicity, the number of years the person has been employed, prior default, employed, credit score, late payment, citizen, zip code, income, so on and so forth. So these are all basically fields in the application form. So like we saw earlier, the machine learning model could reject the application based on late payments. It could reject based on credit score. It could reject based on prior defaults, based on income, based on debt, so on and so forth. So the machine learning model does something very similar to what human beings do. They look at the features and then make a decision as to the application. So one of the simplest machine learning models is a logistic regression model. So what we do in logistic regression is we have a bunch of features like x1, x2, x3. These correspond to the real world features like credit score. X1 corresponds to credit score, x2 to income, x3 through prior default. All these have to be converted into numbers. And these numbers are passed to a summation module. So each of these features is given a relative importance, right? So there is the X1 feature, credit score gets a weightage of W1. The prior default feature, X3, gets a weightage of W3, so on and so forth. So the model determines these weights. And these weights are combined with the features as a weighted sum of the features. Of course, models also have a bias. So that bias is captured by an initial weight called W0. The one that corresponds to W0 is the bias. Bias stems from assumptions, just like the human bias stems from assumptions that certain gender is, or certain religion, certain ethnicity, certain skin color is superior to others. Machine learning models also make some assumptions, but these assumptions are mathematical assumptions. So because of the assumptions, there's a bias in the system, which is captured by W0. So all these weighted features are summed up, and the bias is also factored into the sum. And then to convert that sum into a probability, we pass it through a sigmoid function. Sigmoid function is any function that looks like, that is in the shape of S, right? Here you can see the shape of S. So in math, it can be represented as e power z by 1 plus e power z. This particular sigmoid function is called the logistic function. There are many sigmoid functions which are of the shape S, but this particular function that we are using here is called the logistic function. So we pass the sum through this logistic function, and we get a probability. So as you can see, what we generated is similar to what the human beings did. The explanations are based on the features and their weights, their relative importances. So that is how that is the general philosophy of machine learning models. In most cases, machine learning is essentially finding out the weights for each of these features. It learns, the algorithm tries to learn the weights for these features. So the logistic regression module can be thought of as one unit of a neural network, one neuron. Of course, this function, the sigmoid function, could change to a different function or another sigmoid function, but that's a matter of detail. But the philosophy is that this kind of functionality that we saw on this slide captures one neuron. The first version of ChatGPT had 175 billion such lines, these lines connecting the neurons. There were 175 billion such lines, and each one of them having a weight. So you can understand the difficulty now, right? It's very hard to explain when there are 175 billion such weights. If it is just one weight corresponding to feature, it is somewhat explainable, not entirely, but at least somewhat explainable. If there are 175 billion weights, so that's where the challenge is. Another simple model is linear classification. So logistic regression is a smoother and better version of linear classification. So in linear classification too, we combine the features with their weights. So the weights are basically the coefficients, which are the slopes along the dimensions. These coefficients correspond to the hyperplane that separates the approved and the denied applications. So in machine learning, we all become vectors in space with magnitude and direction. So the vectors, there are two interpretations of a vector. One is that of a matrix with single dimensional matrix with a bunch of numbers as elements. So that is one interpretation. And the other interpretation is the same vector can be represented as a point in space, vector space. So the numbers in the single dimensional matrix correspond to the dimensions in this vector space. So the applicants, the credit applicants, all become vectors in the space. So the features are basically the values across the axis. So the W's in this equation for the hyperplane indicate the importance of the features. So just like in logistic regression. So there is another algorithm. This also is a simple algorithm called k nearest neighbors for credit, and we can use it for credit approval as well. So for instance, we want to know whether John's application, this red star here with a question mark, he's John. We want to know whether John's situation, whether John's application has to be approved or not. So we see that John's situation is similar to Tom, Dick, and Harry's. Tom is the green square, and Harry and Dick are the blue polygons, probably hexagons, right? So Tom's was approved. So the green box was approved, but Dick's and Harris was denied. So that's the reason why they have a different shape and different color. So what is your guess? Should we approve John's application or not? Probably not, right? Because the majority of the neighbors have been denied the credit application. So therefore, the model is going to deny John's application. So typically K is odd. So in this case, you see that K is 3 neighbors, right? So label varies with different Ks. The number K will, typically it is odd. So that is how the K nearest neighbor algorithm works, and it is quite explainable. We are able to explain based on the proximity to the neighbors and the labels on the neighbors. There is another algorithm called decision tree. So in decision tree, what we do is we take this kind of a training data set on the left with which is a kind of table. The last column is the target variable, whether credit is approved or not. And then using some math from information theory, we are going to construct this kind of a decision tree. So whether the person has a prior default, if no, then look at the location. Then if the location is outsider or county, then look at the income. If it is less than, the income is less than 80K, then deny the application. So this is this is how a decision tree is constructed to basically adjudicate on the applications, the credit applications. So this, as you can see, this also is quite explainable. We are able to clearly say why a person's application has been denied or approved, right? So these leaves tell whether the application is approved or denied. So all these contribute, the algorithms that we talked about, the k nearest neighbors, decision trees, logistic regression, linear regression, these contribute towards what are called as anti-hoc explainability. So these models are interpretable by design. But there is a need for post-hoc explainability models also. That means post means ant means before happening and post means after happening, right? So what if the model is a black box? For instance, you take large language models like ChatGPT, where there are 175 billion such lines connecting the neurons. There are several other models which are complete black boxes. It is very hard to interpret what they are doing. So that is a challenge the post hoc explainability methods address. So any idea what we can do? So the question is, can we create a model agnostic method for explaining predictions of machine learning models? So we want a method which does not depend on whether we are using decision trees, logistic regression, and things like that. So explanations are not specific to the machine learning models. Sometimes nearest neighbors or decision trees are not the best way to explain, right? So, and then the advantage of model agnostic methods is that we can easily replace or upgrade models without changing the explanation approach. And explainability now becomes a layer on top of the black box machine learning model. So we are going to run the model first and then apply this explainability method. So it leads to easier benchmarking and comparisons of model interpretability. So because it is model agnostic, it is not dependent on the model, we can have a uniform way to benchmark and compare interpretability. So these methods, of course, have to be post hoc. Explanations are derived from a model after it has been trained, unlike the previous ways of explaining, which are ante hoc. This also helps the model agnostic methods can also help if the features are not human interpretable. So in the previous example of credit application, the credit score, the income, all those were human interpretable. But in many machine learning applications, the features, like in this case, the image pixels, are not human interpretable. So typically the features are the pixel values and they are not human interpretable. 1 million pixels, you cannot understand, right? 1 million numbers or 10 million numbers. These days, if you take a picture on iPhone, it creates several megabytes of pixel values. So you obviously cannot interpret humanly. Similarly, ChatGPT converts, in fact, all these large language models convert text into funny numbers like this one. So they work with numbers like this. And obviously, these are not interpretable either. So what do we do in such cases? So we still need explanations which can be understood by the human beings. So we need to convert the cryptic features Z using some algorithm, some method into human interpretable features. For instance, in case of pictures, it could be the eyes or the mouth of a person or the ears of a person. So those are the human interpretable features. So we need to be able to convert non-human interpretable features like pixels into human interpretable features. And then vice versa should also be there because we want, that's one of the requirement of explainability. I mean, the explanation should be friendly with machines and also the human beings. So we need this kind of a conversion mechanism. So Z is the original features which are not human interpretable, and Z dash are the human interpretable features. So the first algorithm that we are going to talk about is called local interpretable model agnostic explanations line. This is a paper authored by Ribeiro, Marco, Tullio, Samir Singh, and Carlos. The paper is titled, "Why Should I Trust You? Explaining the Predictions of Any Classifier." It was published in the SIG KDD conference of the ACM in 2016. So the idea is it provides local explanations for individual predictions, not global. That means we take just one row in the table, the training data set, and try to explain it. So we don't explain the entire model as such. So that is where the local is coming into picture. And then it needs to be interpretable. That means human understandable. The explanation should be human understandable. That's the reason interpretable is there. Then model agnostic. It works on any model. That means it's a post hoc method. So, and of course, explanations. So it uses a surrogate interpretable model like the ones discussed earlier. So for instance, the ChatGPT is a cumbersome model which cannot be understood. So that is the reason why this method uses a surrogate model. That means it works by approximating the model locally with an interpretable model. So what are some of the interpretable models? The ones that we just discussed, like linear regression or linear classifier, logistic regression, k-nearest neighbors, decision trees. Those are all interpretable models. So it uses such surrogate. Surrogate is basically an approximate, right? Or a substitute interpretable model like the ones discussed earlier. And of course, it is local. So the surrogate model is trained on the data in a local context. So it doesn't look at the entire data set. It looks at a very specific portion of the data set. And that context is typically around a specific data item. That's why it's called local. So we go instance by instance, one row at a time. Yeah, it is interpretable because the explanations need to be human understandable. And it outputs feature importance scores for the prediction, just like before, just like the humans did. The model LIME basically tells you the importances of the features, where the model focused on which features to come up with the decisions. So that is the general idea. So because we talked about local interpretability, I thought we'll also talk about global interpretability. So what is the difference? So the focus for local interpretability is individual predictions, whereas global interpretability explains the overall model behavior. The scope is specific instance for local interpretability and the entire model or data set for global interpretability. The methods used for local interpretability are LIME and SHAP, whereas global interpretability, the ones that we saw just before, like decision trees, and then there are more like the rule-based models, which provide you with a global interpretability for the entire data set. The goal for local interpretability is to understand why a model made a specific prediction of for a data item, and global interpretability is to understand how the entire model works in general across all the data. So the applications for local interpretability are debugging, identifying biases, building trust, and global interpretability is mainly for model design, feature engineering, risk assessment, and so on. So if we realize that the model is, for instance, focusing on the wrong kind of features, then we go back and redesign the model or do a feature engineering all over again, things like that. So that is the purpose of global interpretability. Whereas local interpretability, it's about debugging for specific instances. And the use cases similarly are going to change. So the use case for local interpretability is for loan officers, like the instance of credit denial that we talked about, or clinicians, right? So that's the use case for them, because clinicians need to focus on individual patients. They cannot generally talk about the model. So clinicians need to understand why a particular patient was recommended, say, statins, right? Or some other medication. So they're more focused on individual instances. Whereas global interpretability is important for regulatory situations where trust and compliance are crucial. So, and also for scientific research. And the level of detail, of course, will be, for local interpretability, the level of detail is for specific predictions, whereas global interpretability, some level of detail is sacrificed for comprehensiveness. So, I mean, these are general distinctions, but some techniques like, there are techniques like partial dependency plots and others, which can be used locally or globally. But I just wanted to give you this difference. But today's session will be focused on local interpretability. So let us look at how LIME works. So this is a data set. For instance, let us say for credit application denial or approval. So the pluses indicate one class and the circles indicate another class. So if you look at the decision boundary, it is quite complex. The model is complex. So it's very curved around the data points, right? So we got a new data item, a new application, which is represented by plus. There's this big plus, right? The red color plus. I mean, just because it's plus does not mean that it belongs to one class or the other. It is just a symbol, right? This figure is from the original paper. So I just thought it's a better idea to explain the original paper itself. And the points on the left and right for this line are generated, right? So these pluses and these dots are actually generated. We'll see how to generate these points. So we generate the points around this test data item. So if a new data item comes, we try to generate points. So you can see that the original points are smaller. They're all of uniform size, like this plus, this plus, this plus, or rather this plus, and these two dots. They're all of uniform size, but the sizes of these dots, which are generated, and these pluses which are generated, are of different size. The reason is because the size of the points indicate the distance to the test item. Let us call this as test item. We are going to test whether this applicant's credit will be approved. So how are we going to generate? Let us look at the algorithm itself. So first is we select an instance for explanation. In this case, it is basically this plus point. So we choose this and then generate perturbations around the instance. So we perturb this particular person's features by modifying this particular person's features randomly or adding some random noise, right? So we perturb, we change the features of this. So for instance, if the credit score is 817, then we change it to 921, right? Or if the income is 30,000, we change it to 35,000. So we make such changes and generate these points. So we generate a diverse data set that simulates how the model might behave with slight variance in the input. So that is a key idea here. And then we use the black box model to do the predictions and use these labels, the labels that are generated by the black box model, as labels for this small training data set around the point that we are trying to explain. right? So, then one other thing we are going to do is we weigh the perturbations using a kernel, usually exponential. That means not all points get the same weight. We'll see how to do it mathematically, but intuitively, the intuition is that the prediction for this is not as important as a prediction for this point here. The big pluses are more important than the small pluses. Similarly, the big circles are more important than the small circles. So we assign a higher weight to instances closer to the original input and lower weight to those farther away. Then we are going to fit an interpretable model to the new data and generated labels. So for us, the simple model, we are going to use this as a training data and use a simple interpretable model like linear regression or a decision tree on these points, on these perturbed points, using the distance weights from the previous step. So this interpretable model, this line, approximates the behavior of the complex model in the vicinity for the original instance. So if you see the decision boundary in this instance, the true decision boundary drawn by the complex machine learning model is this kind of almost like a straight line. It's almost like a straight line around this point. So this model, this linear regression model, approximate, or linear classifier model approximate the that decision boundary only around this point, not elsewhere. So then once we get this model, we generate the feature importance, right? So so we analyze the coefficients because it's a linear model. We analyze the coefficient, or for that matter, if you are using a tree-based decision tree kind of model, you are going to analyze the feature importances generated by the decision tree. Then we need a human readable format. So we visualize the explanation. So either we use a bar chart or a pie chart showing the contribution of each feature to the prediction. So to weigh the points around this test point, the paper, what it does is it uses an exponential kernel. If you are familiar with the normal distribution or support vector machines algorithm, there's something called an exponential kernel. So the intuition is, so it is given by this formula. The intuition is that if this red dot is the point, the importance of the points decreases exponentially with the distance. So this x minus x dash is the distance from the point x. So the distance exponentially decreases with, I mean, the influence of the point decreases exponentially. So, so that is the idea that the paper uses. So to weigh these points around the test point, there is an exponential kernel that is applied. So this is an illustration of the same effect. So as we go farther away from the centroid of the cluster, the confidence of or the importance of the data point decreases smoothly and exponentially. The value, this is for the, I mean, in support vector machines, this is called an RBF kernel, but it is essentially an exponential kernel. So the value of the kernel is maximum at the center where the distance is 0, because e power 0 is 1. So now let us take a peek into the math. It's not too difficult. So the loss is locally weighed. The loss function is given by this L. There's a local weighting by this pi. So we'll see what each of these symbols mean. So F is the black box model, like the ChatGPT or the complex model, which is hard to understand. G is a surrogate interpretable model, such as the linear regression or logistic regression, decision tree, and things like that. So F of Z is basically the prediction of the black box model. G of Z dash, remember, we want interpretable features. So when we apply the interpretable model, the simple model, we are going to use understandable features, not the original features. It could be possible if the data is tabular like credit application, then Z may be equal to Z dash. But in general, we want to make the prediction using the interpretable features when we are using the surrogate model. So that is the idea of F and G. And then this pi xz is the local weight for the points around X. So remember we generate points around X. X is the point that we are specifically considering. So this is given by the exponential kernel, like we talked earlier. The effect is that the influence of the point decreases exponentially with distance. So the importance that we give to farther points is exponentially decreasing. So this is so Z is basically the vector. This R power D basically means it's a vector. That means there are D number of real numbers. Is a sample in the perturbed set Z. So that is pi x. We already talked about FZ. Z dash is the interpretable version. We already talked about it. And then the explanation is given by the is produced by minimizing the loss function. So we are going to look at all the interpretable models. So capital G is the list of interpretable models like decision trees, logistic regression, and so on. For each interpretable model, we are going to minimize the loss. This loss is the same as this one, but there is an additional term called omega. So, so what is omega? Omega is the regularization. I think it's given in the next slide. Okay. Omega is the regularization parameter, right? So if you know L1 regularization or lasso regularization, you must be knowing this regularization parameter. The effect of adding this is that some of the weights for some of the less relevant features will become zeros. So what is the advantage of this? The advantage is that if there are, say, 100 features, if there are 100 columns in the tabular in the table, it is very difficult to wrap our head around with 100 different weights, right? With one or two weights, it's much more easier to understand. For instance, if we say that the credit application is denied because of the credit score, then it is easy to understand. If you say that it was denied because of 10% income, 20% credit score, 30%, and so on and so forth for 100 features, then it is very difficult to wrap our head around. So that is the reason why we add this term called regularization term. The omega G is the regularization term. So in case of regression, it is typically lasso or L1 regularization. In case of decision trees, this could be the depth of the tree. So we try to keep the trees, we do not grow the tree too much. We are going to prune it off at some level. So the idea is to reduce the number of interpretable features. So that is the only idea. So you minimizing this loss function along with the regularization parameter. So folks who are familiar with statistics might recognize the term shrinkage, right? So the omega G is basically the shrinkage parameter in statistics. So minimizing the loss, we get the explanations. So the C is this Greek letter is the explanation generated. So, so that is the idea. And so G, we already talked, is a set of interpretable models. Omega is the regularization parameter. So using this algorithm, generating local interpretable model, surrogate model, and all that stuff. Now, once we generate this kind of a model, this kind of straight line model, it is very easy to interpret because the coefficients of the equation for the straight line are the importance for the features. So it is quite easy to come up with these visualizations. So this paper that I talked in the beginning of the session, we observed that, so the left-hand side is a specific instance. So this person is aged 40, you can see the age here, 40 years. And this person does seek help for his mental problems. He does not, he or she says that the mental issues do not interfere sometimes, do not interfere often, and so on and so forth. So these are all collected in a form, survey form, right? So this is the person that we are trying to, that plus, the big red plus is this person, right? So now, so interestingly, this person takes help, right? It says that, where is that? Yeah, here, where was that? Seeks help is yes. So this person is seeking help for mental issues. But the model predicts with high probability, 95% probability, based on the fact that there's no interference to the work. It predicts that the person does not have mental issues. It predicts a 0, right? And the importance given, the importances of the features, these are all the features, basically the answers given in a survey form. So these are all the features. And if you look at the features, importance to the features, you will see that interference with in work, interference in the work sometimes is given the most importance, even more importance than the importance than the interference quite often, right? So you can see the non-intuitiveness of the model, right? We achieved a great accuracy, but the model is focusing on wrong variables, wrong features, and then making a wrong prediction in this specific instance. I mean, mental health is a very serious issue, right? So this is the plot produced by Lime. It gives you the feature importances of individual features. One color indicates the importance towards one class. The other color indicates the importance towards the other class, and it gives the numbers also measuring the importance. So we can see that if the mental issues do not interfere with work, it is given the highest importance, even if the person says that he is seeking help. So that is the fallacy here that we observed with the machine learning models. So that's the reason why in the conclusion we mentioned what I stated earlier. So we are also using Lime for explaining object detection. As you can see, the pixel values are not interpretable, but Lime does a good job in interpreting the human readable feature. I mean, converting the non-interpretable features to interpretable features. For instance, it can show positive regions in recognizing this as a bird, and the negative regions in playing a role. So this work is still under under review actually. So I cannot talk a whole lot about this. Um, and then, so there is another technique called Shapley additive explanations, but I think I don't know if I have time. So do I have time to cover this, or shall we conclude quickly?
We shall conclude.
Okay, so we'll conclude. Okay, so in that case, I'll skip these slides and then talk about the future directions. So one future direction I feel is important is to um, uh, come up with explainable reinforcement learning. Right, reinforcement learning is used in more complex real-time environments like robotics and autonomous systems. Right, so it's important that we come up with explanations for reinforcement learning, and we need more intuitive, visual, and interactive explanations. So interactive interfaces can enhance the explainability. So as you can see, the explanations were visual but not as interactive. So that is one area. And then some kind of reinforcement learning with human feedback for explainability to improve the explanation. So there's an explanation generated. There should be some feedback from the humans to explain, to improve the explainable explanations. So that is another probably research area. Then aligning explainability practices with compliance standards. We saw GDPR has a substantial focus on explainability. So we want to integrate explainability more into the compliance standards. And then the explanation should be able to change in real time. So you're driving a car and the self-driving car, sorry, you're going in a self-driving car and it took some decisions. We want explanations for those decisions in real time, right? So based on the context in which the decision is made. So that is another area of research. Then, then there's plenty of scope for combining ideas from fields like cognitive science, ethics, and human-computer interaction to enhance the explainability methods. And explanations that are tailored to the user's expertise and needs. We want the explanations to be very specific to the user's needs. So these are some of the research questions, and I'm happy to answer any questions.
Thank you so much, Dr. Vishnu. This was a very impactful lecture, and the importance of explainability cannot be underestimated in the current times, in the current climate. Does anybody have any question for Dr. Vishnu? So, Dr. Vishnu, you mentioned ChatGPT and you elaborated on the amount of neurons, um, the amount of connections that were used in the first ChatGPT going to 125 billion. In that kind of situation, how important or possible is explainable AI in deep learning models? You know, because in the current ChatGPT, for instance, we have some large language models with trillions of tokens. You know, the neurons are everywhere. So how can we use what current state of the art techniques are available out there for explainability for these large language models?
So for deep learning models, sorry, was there a question? Okay, so for the deep learning models, there are other techniques as well, not just the ones. I mean, you can still use these techniques. These are post hoc. So these can be, and model agnostic. So you can use the techniques like SHAP and LIME on those models as well. But there are some specialized techniques there's a technique called LRP. I don't exactly remember now, but so there's a technique called LRP, so which can be used specifically for deep learning models. And then this topic, there's another concept called mechanistic interpretability, which is coming up really well. There's a lot of interest in that area as well, which can be used on large neural networks. So it's an active area of research. So which is still under investigation. But until that time, we have all these tools, post hoc explanations like we used. So for instance, in a recent paper, um, we in a recent paper that we published explaining misinformation detection using large language models, we uh, we explain the large language model classification using line, right? So you can see these are all words. The words internally are uh, converted into vectors, vector embeddings, but you can see that they are converted back into words. Uh, the features are converted back into words. We can see what words are playing a role in the positive or negative prediction made by the large language models. So the technique that we taught, LIME, can be used. So LIME and SHAP can be used with large language models also. I hope that answers the question.
Yes, thank you, Dr. Vishnu. Someone in the one of the attendees said they want to see your shapely or sharply slide. Your slide on sharply.
Yeah, so I can go over, but so I don't know if you have time for that, but yeah, what I had was, so this is also a model agnostic um, model agnostic method. It was authored by Scott and others in 2017. So it's based on cooperative game theory, specifically using Shapley values. So Shapley values treats um, each feature as a player in a game. So it can be used for explanations at both global and local levels. And the model prediction is the sum of the sharp values for each feature and calculates the average contribution of each feature to the prediction by considering all possible subsets of feature. So this is coming from Lloyd Shapley values. So some of you may be knowing that Lloyd Shapley won a Nobel Prize for this his game theory, his inventions in game theory. He was a professor in University of California in Los Angeles, I believe. So the paper was published in 1953, and the goal was to distribute total gains among players in a correlation based on their contributions. So, so the idea is that each player gets their fair share of the total gains based on their marginal contributions. So for instance, player A's contribution may be a result of teamwork with player B, right? So that is the reason why we need to consider subsets of players, correlations of players. So considers all possible correlations of players and their interactions. So order independent, proportional weighing, fairness is key here. Um, So we come up with these feature subsets like this. So for instance, for credit application, if these are the features on the top, then we come up with subsets of all these features. And we basically apply this formula to come up with the uh, feature importance. So for each feature, subset of the features S, we are going to compute this. So phi I is the feature attribution for feature I. X is the specific data item. F is the set of all features. S is the feature subset under consideration. F is the black box model. And the F of the subset with the feature I of X with the feature I minus the prediction without the feature I is the contribution of the feature I in the subset S. That is quite intuitive, right? We remove the feature, compute the prediction. We include the features, compute the prediction. The difference will give the contribution of the feature. So that is the idea. And we do this for all subsets. We also view contribution by this combinatorial. It's the inverse of the combinatorial. If you look at this, this is like inverse of the combinatorial of choosing S number of features from a total number of features F. So that's the weighting factor. And don't really, it's hard to remove features in once the model is constructed, right? So what we do is, instead of removing the features, we insert a random number in that particular feature. If it is randomized, then it makes no sense. So that's how we compute feature importances in SHAP. But the idea is basically computing the feature importances using a different kind of method, using the Shapley values. So we generate, for the paper that I talked earlier that we published, we generated this kind of Shapley visualization, Shapley value visualization.
Okay, thank you.
That is the idea.
Yes. Dr. Celestine has a question.
Yeah, Dr. Vishnu, thank you. In this same figure, good you brought it out. I wanted to ask you a question. Very, very nice that you were able to pick psycho-intelligence that we are working on, you know. You mentioned in this same research, you said that you people predicted mental issues to be 0. Because in psycho-intelligence, you know, there is a level of madness in everyone. That's one of our analysis. There's this level of madness in everyone. So I don't know how you got the madness, mental issues to be 0. Because the research we are working on, we are believing that that degree of madness can be cured, you know, depending on explainable issues, you know, as we go on. So I was a little bit brought aback from that analysis that you made.
So you're saying that every person
every person has a degree of madness. So that is what we are working on. But it depends on at what level does it become a problem.
Yeah.
Because when you say it's 0, what are the features that made you people say it's 0? You know, people can have breakdown, they can have suicide thoughts, they can have mental breakdown, and that is what we are trying to do. You know, when it's like checking blood pressure, and then suddenly you know your blood pressure is coming down, you know, and then you start, or your blood sugar is coming down, you try to like take a chocolate or something to improve it, you know. So when you know that you are being tense, how do you calm down, you know, to make sure that you don't go overboard?
Yeah, that is deep into psychology, I think, but intuitively, right? If you know that a person is taking help for mental issues, and then just because it's not interfering with his work, classifying the person as not having mental issue is quite worrisome, I think. But more importantly, see the fact that the issue is not interfering with work sometimes is ranking more than that it interferes often is also not intuitive, right? So if it is interfering often, then that is what should weigh more than sometimes. But the model is doing the other way around. So that is an inconsistency. But that's a good point that you bring up. Yeah, seeking help alone is not the only deciding factor.
Okay. Thank you, Dr. Vishnu. So now I want to call on the head of School of Creative Technologies and Arts, Sam Johnson, to give the closing remarks.
Thank you very much.
Sam.
Thank you very much for that introduction. Thank you, Dr. Pendyala. That was a fantastically informative and useful talk. I'm sure our students and colleagues that are attending this evening and our external guests found that incredibly useful. It's wonderful to see this is the first of our series of November to Remember. We have 2 weeks of fantastic talks, but what a great inaugural discussion we've had there. So thank you very much for joining us again, Dr. Pendyala. And thank you to the organisers and also to all of our students and guests this evening. So I think it just behoves me then to say thank you very much. Larry, are you able to bring Dr. Pendyala's award up on the screen? Is that possible?
Yes, it is.
Absolutely fantastic. So thank you, Dr. Pendyala, for joining us again, for sharing your expertise, for giving us so many useful insights into this incredibly important field, and really underlying the amount of work that needs to be done regarding the reliability of different models in a whole range of different sectors, actually. And we look forward to working with you in the future, of course, both in terms of developing research, but also we do hope you'll join us again to speak to our colleagues and students. So perhaps everyone could give a round of applause to Dr. Pendyala and a big thank you for sharing your time with us. Thank you very much.
Thank you so much for the opportunity, and I look forward to working with you again.
Lovely. Thank you, colleagues. And we'll see you tomorrow for another fantastic lecture.
Yes. See you tomorrow.
Thank you. Bye-bye. Thank you, Vishnu.
Yeah, thank you so much for the opportunity.
We'll see you on that is next week.
Yeah, the 14th, right?
Oh, 14th, yes, 14th.
Yeah.
All right. Thank you.
Yeah, thanks.
Okay.